All right. It's looking like we should have a hassle-free broadcast today with no viewers coming online yet, so no one to appreciate, but it'll be there when you check later. Whoops. All right, welcome everyone. If you want a copy of a handout of today's slides and don't have one already, they're sitting there at the front. It's looking like we should have a hassle-free broadcast today. No viewers coming online yet, so I don't need to appreciate that it'll. All right, so we're going to be moving beyond descriptive statistics today and doing one class on probability. It's the only lecture on probability in this sequence. After this, we're going to be moving into statistics and inference. But this is a fun one. Bayes' rule is for the smallest bit of probably some of your best bang for your buck for a little bit of math and being able to do some really interesting, useful things with it, I think. So I'm going to start out with an example today in the application of Bayes' rule to screening tests, go over some of the calculations around screening tests, most important being sensitivity, specificity, positive predictive value, negative predictive value, and population prevalence, and all of the relationships between these. And then with that as the motivating example, go over some properties, general properties of probability, introduce the concept of conditional probability, and introduce you to Bayes' rule. So let's start with this example. I guess I have a couple examples already. So suppose we have a screening test that if you have cancer is 100% certain to detect it. Okay, so it will never tell someone who has cancer that they do not have cancer. Now, let's go and take this test and apply it to a population where there is a prevalence of this cancer type, say, of 5 per 1,000. Now, in that population, if someone receives a positive test, what do you think that the probability is that that individual has cancer?
0.05%.
I heard 0.05%. I heard 50%. Want to give me what makes you either of those reasons? Why do you think that? Yeah.
I said 0.05 because if the prevalence of cancer in the population is 5 per 1,000,
Mm-hmm.
that would be not 5%, but 1, however you say that. So
Okay. So 0.05 is the prevalence is the 0.5%, right? So that's the prevalence in this population. So if this test predicted that you have cancer in every single case, like it's just a sheet of paper that you show to everyone that says you have cancer, then that would be the answer. So that would be a terrible test, but that is a possibility. But this gets at any other thoughts about this before I
was thinking it gives you 100% if you do have it, but if you don't, there's a chance to give you a false positive.
Yep.
So, I mean, yeah, so there's a 50-50 chance. Well, I mean, it's probably not 50-50, but
right.
There's a false positive chance among the not having.
Yeah, that's right. I mean, in this first example, which is a good case, the case that predicts cancer for every single person, if the false positive rate is equal to whatever the control rate or the non-cancer rate in the population is. Yes?
Wait, isn't the sample 5?
Isn't it 5?
For this question? Because the question is asking what is the probability that an individual testing positive? So you're
Yep.
saying that already tested positive, and the screening test is always correct.
No, for positive.
No, I'm saying that we know that the general prevalence in the population is 5 per 1,000. We don't know which 5 here it is. We don't know for sure that there are 5. It's just that that in this untested population, there's a prevalence of 0.5%. So it doesn't mean that they've been given this test already. Prevalence.
I see what she's saying about
But
the
if
wording,
they're-
though, because
yeah,
it
the
says
wording-
if the test is applied to the general population, what is the
Right.
probability that an individual testing positive
Right.
So you've already given them the test, and the test is always correct, so they're always going to have that
It's
cancer.
only correct for positives, though. It can be
Right.
It can be positive for somebody who doesn't have cancer. False. If you have cancer, yeah, it definitely works.
I get it. I think the wording.
Yeah. So the key thing in the wording here is the probability that an individual testing positive. That doesn't mean they are positive. It just means that's the outcome of this test. We don't know if they have cancer or not. Then the idea of this usually is that we have this screening test that we can apply on a large scale, and then we have some other much more expensive gold standard test that we can follow up with that will give us the right answer. There's another question?
No, I was trying to explain.
Yeah. Okay. Any other thoughts about this? I've got the answer on the next slide. And it's not really the answer. I have no idea what the probability is. There's not enough information here to say. Between the extremes, if we have the sheet of paper that just always says you have cancer, then we heard what that probability would be. You would only have a 0.5% chance of actually having cancer. To the very other extreme, where it never makes mistakes on negatives, in that case, that individual has a 100% chance of having cancer. So it's anywhere between 0.5% and 100%, depending on how good the test is. Question?
Yes. So I think my confusion always comes because I've seen prevalence and probability be used in a very similar way, and I think that they're completely different things. And so sometimes I get really confused when I see them kind of being used interchangeably.
So prevalence is a very particular probability. Probability can refer to a lot of things. Prevalence is the probability of an individual having whatever condition you're talking about in the population in the absence of any other information. So we also sometimes call it the prior probability. So I haven't said what probability I'm talking about here. This would be what we would also refer to as a posterior probability. That is, it's based on the prevalence, the prior probability, plus some extra information from the test, giving us this post-test probability that an individual has the disease. So, and we heard, was it you, Leonard, who mentioned, sorry? Leonardo, thank you. That what really matters here is how the test performs on people who do not have cancer is going to determine what it means to you when you test positive.
You have a message.
Oh, I have a message. Thank you. Oh, the PowerPoint screen is black? Seriously? Jeez. Okay. I'm going to... Okay, I'm going to try and solve this right now.
There's another one.
Come on. Huh, that's sure. Okay. That seems to have helped. That's what I was doing before. I think that that's a bad thing for some reason. Okay, now sound.
That's probably not good stuff. That was fine before.
Let's see. Hello. Okay, no, sound is broadcasting. That is not on a problem on our end because I can see the green dots.
It's used to work now for that.
Oh, okay. Oh yeah, the screen does weird things.
It says it's back.
I can see it flashing now. Okay, I'm gonna try. Try this. Yeah, this is a great feature.
It's like memorizing.
Okay, so that seems a little better. Except I still get some odd flashing. Okay. Okay. I think the screen should be good now. All right, so in a perfect world, we would have a 100% accurate test. That's not what happens, though. What we have is tests that are more likely to give you one outcome if you have the condition they're testing for than if you don't. But they can give false positives and they can give false negatives. This is what all of the topics around sensitivity, specificity, positive predictive value are about. And as I mentioned, this gold standard, this is the expensive follow-up test that does give you the right answer, but that is not feasible to give on the larger scale as a screening test. So an example with cancer might be the PSA test for prostate cancer for men, the prostate-specific antigen, which is a protein that can be secreted by prostate cancer into the urine. You can test for this. It's cheap. It's easy to do. When the level of PSA rises, it means that you may have prostate cancer. The way to be more sure about this then is to actually have an oncologist take a biopsy, have that reviewed by a pathologist. Very slow, expensive process. But if you're at high risk of having prostate cancer, then it becomes worth doing. All right. So here's an example with chlamydia infection and a test for the disease. We have two different clinics here. And this is to show you the importance of population prevalence in so-called positive and negative predictive value. So we have this is an STD clinic where there tends to be people who go in there because they suspect that they have an infection, and then in a private practice, which is just more general screening, people are going in not because they have symptoms, but they just are there and getting tested, and there tends to be a lower prevalence. The same test, the same screening test, will have different performance in these two situations. So the PCR test, this is polymerase chain reaction. This is it's a very sensitive test that will pick up DNA that is specific to the chlamydia virus. And this test, it is predefined. You run your sample through a machine. It gives you a measurement. If it's above a certain threshold, you decide that that's a positive test, and if it's below that threshold, you decide that it's a negative test. That's independent of the clinic. So these rows are showing an application of the test to these clinics. The columns are showing the truth according to the gold standard of the condition of the patients. So you see in the STI clinic, we've got 300 positive, 700 negative for a prevalence of 30%, and in the other clinic, we've got 30 positive, 970 negative for a prevalence of 3%. Now, the result of the PCR test, here on the first row, we're seeing the performance of the test on the negative cases, and on this, we're seeing the performance on the positive cases. So the positive predictive value, this is the thing that is of most interest to the patient. And what it means is if you receive a positive test, what is the probability that you actually have the condition? So we can get that by reading. We want to look only at the people who receive the positive test, and then from the gold standard, we calculate here the probability that the person actually has the infection that the test has given a positive result for. So in the STI clinic, the positive predictive value is 294 over 315, which works out to about 0.93. In this other clinic, where we have a much higher proportion of true negatives, it works out to 29 over 58, about 50%. So this is the same test being given to populations with different prevalences, and we see very different positive predictive values. Now, I have some examples from the newspaper and published literature coming in later where this is something that is not properly appreciated by many people, that your performance of a test does not just have to do with that test, it has to do to the population to which it is applied. Question?
I'm reading this. So on the STD clinic, you're saying, they came in, someone in the clinic thought that they had chlamydia.
Right.
And that's the ABOX, and then the PCR test also confirmed it as positive. And then someone thought that they didn't have chlamydia.
Sorry, this ABOX, this positive is the truth. It's the result of the gold standard test.
PCR confirmed it.
Right. Right.
And they didn't have chlamydia in the V box, but PCR said it was positive still.
That's right.
Okay.
Yeah. Yeah, so these are the people who really have chlamydia. 294 of them get a positive result, 21 get a negative result. Wait, sorry. These are the people who really have chlamydia. This row, these are the people who get a positive test. The rows are the results of the PCR test.
Okay,
So these are all of the people who got a positive test, and 294 of them really had chlamydia. Okay. Sorry for the temporary confusion there. So this is a case we don't actually, this is a kind of theoretical example here, because normally we don't know everyone who comes into the clinic, all 1,000 of them, we don't know whether they really have chlamydia or not. All we have is the outcome of their test. Okay, so a couple more definitions before we move on. An event, this is a definitive outcome, like the result of the PCR test. It is, there may be a random component to determining it, but after it is done, it is yes or no, or something like that. It has a result. So, for example, the individual has chlamydia infection, they have a positive test, someone survives past 70 years of age. So this is a result that eventually at some point in time we have the answer to. And the probability reflects the uncertainty in an outcome. So for example, there are different interpretations of probability. It could be a probability of getting chlamydia over a certain period of time for someone who does not have it at the beginning. It could be the probability of one individual in a population having chlamydia in a cross-sectional type of study. And it could be, for the other examples, probability of surviving past a certain age, or that sort of thing. So an event is definite. Probability is something that we don't know, but we know something about the outcome on average. So in the chlamydia test, the intrinsic properties that are important that we need to describe the test are its sensitivity and its specificity. So these do not have anything to do with the population prevalence. These are just properties of the test. So the sensitivity is the probability that if you have the disease, you get a positive test. So that's the thing that on the first slide of this lecture was 100%. That was a test with 100% sensitivity. Specificity is its performance on individuals who do not have the disease. So that it's kind of the reverse. If you don't have the disease, that's the probability that it correctly says you don't have the disease. And that was the piece of missing information that we had, that we didn't have on slide 2. Okay, another example to type 2 diabetes. This is a real example. It's an important public health problem, and something that is prevalent in the population of elderly U.S. adults, and something where detection of it can lead to earlier treatment and better health outcomes, and where the gold standard test, this drinking of a glucose solution and then drawing blood, this is expensive, time-consuming. It's not something you can do to the general population, and so there are screening tests for it. This is kind of a diagram of what that test might look like if we had all of the answers. So we're divided here into a population of diabetics and non-diabetics. So this is the truth, something that we don't know in the general population, but we're supposing here for illustration that we know it. And here's the screening test that for diabetics, it tends to give you, and it being blood sugar, diabetics tend to have a higher blood sugar level than the non-diabetics. But as you can see, there's a certain amount of overlap here among them. So if we were going to calculate here sensitivity and specificity, we'd fill out this little 2x2 table here, where for the diabetics, it's the number of people who get the positive test. Those are the ones above this line, and the number who get a negative test below this line, and the same thing for the non-diabetics. So the sensitivity is the accuracy among those who have the disease. So among the diabetics, it's 17 out of 20 correct. And the specificity is the accuracy among the non-diabetics, 6 out of 20. It's correct on 6 out of 20 for an accuracy of 30%.
So does that mean that your test specificity is 30%?
It depends. It depends on what you're going to use it for. If you were going to use this in a general population with a prevalence of 1%, it would not be a very good test. It might be a good test with a higher prevalence population. It's certainly a test that gives you some information about diabetes. So if it's something that's very cheap and easy to do, it might be a useful test if you have another way to follow up with it. But that's something, it's a cost-benefit analysis. Does this make sense to everyone? Sensitivity and specificity. So these just depend on the test, not on the prevalence. Now, depending on your objectives for using the test, you might instead want a higher specificity. And this demonstrates how there is a trade-off between sensitivity and specificity. We can move this threshold up so that we give fewer people a positive test. So it's exactly the same test, but we're just changing the threshold of what we consider to be a positive test. And just by doing that, we've changed the sensitivity. The sensitivity has gone way down. So it means we're less able to identify the positive cases. But the specificity has gotten better. So by calling more people negatives, the accuracy on the negative cases is better. So the key thing here is that there's a sensitivity-specificity trade-off. You can move this threshold. If you move it up, you'll lose sensitivity and gain specificity. That's the trade-off for a given test. If you want to improve both your sensitivity and specificity, you need a different test. You need a better test. So that was a nice, illustrative example. In real life, in a real population, there's no line there. All we have in the example of blood sugar level is a continuous measurement. It's a quantitative value. We don't actually know who the diabetics and non-diabetics are, so there's no line in the middle. And in fact, there's no, so we had the diabetics and non-diabetics shaded, but without knowing who they are, we have to get rid of the label. This is what we actually see when we observe a real sample from the population. So what we will get when we go to the new test, all we're going to get is our blood sugar level, and we're going to have a threshold that we determined from some previous test population, probably from a clinical trial. And then we're going to get predictions for all of these people where we do not know if they have diabetes or not. So again, with the low cut point, we end up missing people who have diabetes. With the high cut point, with the low cut point, yeah, we tend to miss people who actually have diabetes. We miss fewer people when we raise the cut point, but we're also going to have more false positives. We're going to tell people they may have diabetes when they don't. Here's the summary for your notes that I think we've talked about all of these already. Questions about this so far? It's fairly intuitive stuff when you start looking at it with some graphical examples like this. See if it remains intuitive as we get into some other examples. Once again, the sensitivity and specificity, those are properties of the test. There's a trade-off between them for a given test depending on where you set the threshold. And then positive predictive value and negative predictive value, which is like positive predictive value, but for the negative cases, those are properties both of the test and the population. So positive predictive value means your probability of having the disease given a positive test. Your negative predictive value is your probability that you don't have the disease given a negative test. So you can start hearing why I need to introduce conditional probability, because those are all conditional probabilities. Okay. So as I mentioned, this has caused actually a lot of problems in the literature. There are other reasons behind these as well, but this has happened over and over with good tests that are applied to a very low prevalence disease, prostate cancer, breast cancer, mental health screenings here. So these are being applied to a healthy population, and you end up with a lot of false positive cases. And in some of these cases, the consequences of a positive test can be bad. They can result in risky follow-up procedures to determine by the gold standard whether you have the condition. Social stigma in the case of mental health screenings potentially. And this is part of this whole cost-benefit trade-off is discussing at what level, at what prevalence in the population it is actually worth using these tests. Okay, let's get into a little bit of probability and a little bit of math here. This A union B, this is the probability of either one of events A or B happening. So as an example, the Yankees winning and the Mets winning, those would be two independent events, and the probability of either one happening is going to be higher than the probability of just one of them happening. The upside down U, that's intersection, that is the probability of both happening. And the probability of both happening is going to be less than the probability of one of them happening. This superscript C, that's a complement. So that would be P of A plus P of A complement. That would be like the probability of the Yankees winning plus the probability of them not winning. One or the other is going to happen if you don't count for things like rain events or such. So the sum of those probabilities is 1. Now this last one with the vertical bar, that's the conditional probability. The probability of A conditionally on B being true. So this would be like the probability of the Yankees winning given that they're playing at home. That's a case where the P of B is them playing at home, and A being the winning. And potentially in that case, it depends. The outcome of A depends on the outcome of B, and that's a conditional probability. These are called Venn diagrams, which are often useful in understanding probabilities and the overlap between them. So A and B here, we draw the intersection of them in the middle. So this circle is the space in which A has occurred, and this circle is the space in which B has occurred. So you imagine if you have a case where A and B have both occurred, then you would put that in the middle. If neither of them have occurred, you put it outside somewhere here. So it's just a graphical representation of probability. And you can extend it. It starts getting a little complicated, but to three events. A, B, and C. A intersection B means that A and B have occurred, but C has not. Does that look okay? All right. I have a couple questions for you now. So, using the notation that I just showed you, go ahead, if you have the handout, write in here how you would write each of these probabilities, the parts that are shaded in green. As soon as you have one, you can call it out to me, and we'll talk about whether that one's right. So how about this first one? Yeah, the first one's just P of B. That's right. Union. That's right. The second one is union. So this is the right side up U question.
Can we go back to number one?
Yep.
Isn't it B and A union B?
Number one, this probability, this is it. All of B is shaded, regardless of whether it's in A or not. So it can most simply be written as P of B. There are other more complicated ways you could write this. For example, this could be P of B plus P of A minus P of A intersection with B complement, or something like that. Like you could add up the area in A and B and then subtract out this area, but most simply it's just P of B. What did you think it might be?
Well, because that center area is shaded, I would think that would correspond with A, I don't know how you say the upside down view.
Like this in 6, this is
Yeah.
A intersect B.
So to me, it would make sense that it would be A intersect B as well.
Well, if you did P of B plus P of A intersect B, then you would count this middle area twice. So you'd end up with an answer that was too large. Okay, so we've got P of B, we've got union here. What about 3? Yep, that's just A. All right, what about 4?
Could you write it as like P of B minus P of A intersection?
Well, you don't want P of B in it.
What you just said.
Yeah, so it could be P of A
Sorry,
minus
P intersection or PA intersection.
Yep, that's right.
And then minus.
That's enough, because P of A would be this whole circle, and then you subtract out the intersection. And 5, that's basically the same. Anyone? Oh. I'm going to. The question here is, can you give a different example of A complement? So the canonical example is the coin flip. If A is getting a heads and B is getting a tails, then the probability of A is 0.5 and the probability of A complement is 0.5. But if it's a weighted coin, so that the probability of getting a heads is 0.6, then probability of A complement is 0.4. With a die, the roll of a die, probability of getting a 1 is 1/6. The probability of getting not a 1 or 1 complement is 5/6. Yes, question?
Yes, for all I did just probability of A intersect with B complement instead of like minus blah blah blah.
Let's see. Sorry, for which one?
Number 4.
Number 4. What do you think it should be?
Probability of A intersect with B complement
Yep, that works.
instead of like minus.
Yep. Yep, and it turns out that this is one of the rules of probability. We'll write down that those two things are equivalent. So this could be probability of A intersect with B complement, or it could be probability of A minus probability of A intersect B.
Right, that is a conditional probability.
So the question was, could we write this as a conditional probability? Yes, we could.
Right, so
Um,
the probability of A when it's not B.
this would, no, it's not that conditional. Let's get to that after we do Bayes' rule. Another question.
I just wanted you to go over that, her response. You said that could be A minus B.
Yeah, I wonder if I can,
No,
I
intersect.
can't write.
Not minus. I'm sorry.
So this could be if A is true, so it's in this circle, and not B or B complement is true, meaning it's outside of this circle, then that describes this green shaded area. So A and not B is a description of this green shaded area. An equivalent description is A minus this area, which is A intersect B. Was that your question? All right. Questions? Any more? Okay. So we can have mutually exclusive events. So chlamydia, that's a mutually exclusive event. You either have it or you do not. The Yankees winning on a given night, that's or losing, those are exclusive events. And we have some rules about those. For exclusive events, the probability of the union, so C, in this case, C plus C minus, or this could be C plus C complement, is just the sum of them. So there's no intersecting region that we have to subtract for the union. And if these are exhaustive, as in there's no other possibilities, then that sum's equal to 1. Make sense? And conversely, the intersection is 0 if they're exhaustive. There's no intersecting region. For non-exclusive events, so we have some overlap. For example, let's say having chlamydia and having heart disease, they're not exclusive. If we want to write this union, now it's not just the sum, it is the sum minus this area, because otherwise it's getting double counted. So it's the sum of the two probabilities minus the intersection for non-exclusive events. So this is generally true, it's just that for exclusive events, this intersection probability is 0, so it just disappears. And this intersection is equal to the probability of these two events independently if they are independent events. So if having heart disease has nothing to do with having chlamydia, then you can calculate the intersection by the probability. Or sorry, by the product of those two probabilities. So conditional probability. So this is the condition, the probability of for example, event A occurring given that event B has already occurred. You can say it like that, or say the probability of A given B, or A conditional on B. And we use this vertical slash to mean a conditional probability, or a given. And an example here could say, for example, be the probability of having chlamydia given that you have heart disease. And if those are independent events, then that will just be equal to the probability of having chlamydia. If they're not independent, then this will be the relationship. So it's the probability of both of them happening. It's the intersection divided by the probability of B. And when you look at it, diagrammatically, the intersection looks like this. The probability of B looks like that, and this is really just a, you can imagine this. So in the case of the probability of having chlamydia, given that you have heart disease, it's the probability. So you have to have both, right? You have both chlamydia and heart disease, and then it's just divided by the probability of you having heart disease of the given event. Which brings us to Bayes' rule. Bayes' rule, it's a really simple derivation actually, and it comes from the transitivity of the intersection. So the probability of A and B is the same thing as the probability of B and A. It doesn't matter in which order you write those down. And then from that, the equation for conditional probability that I showed you on the last page, you can write these two things as followed. So A intersect B is A given B times P of B, and the probability of B intersect A is probability of B given A times P of A. Just two ways of writing the same intersection of probabilities. And then you divide this through, so divide through by the P of B, and that gives you Bayes' rule. That's it. So it relates the conditional probability of A given B to the conditional probability of B given A. And as you're going to see, you can use this for converting between, if this is a sensitivity, this can be a positive predictive value. So it allows you to convert back and forth between probabilities of a screening test and its performance in the population. These are just some terminologies that statisticians like to use for these yes questions.
Can you repeat that? P, B in condition of A is the sensitivity of A, and and then with B, A condition on B.
Sorry?
You just mentioned that the E
Yeah.
probability of B in condition of A
Yeah, this.
is the sensitivity of A, right?
So so sensitivity was the probability of having a positive test given that you have the disease. So that here A would be whether you have the disease, and B would be getting a positive test.
So just the numerator is
Mhm.
the sensitivity.
This would be the sensitivity. Then this would be your probability of having a positive test given that you have the disease times your probability of having the disease divided by your probability of getting a positive test. And then that would tell you your probability of having the disease given that you got a positive test. This P of A given B here gets called the posterior probability because it is a product of the prevalence, which would be your prior probability. So with no information, the best guess you can make is that you have the same probability as anyone else of having the disease. So that's why this P of A is called the prior probability. This P of B given A is the likelihood. So in this case, it's the likelihood of a positive test given that you have the disease. And this P of B is a normalizing factor, or it doesn't have as direct an interpretation. In this case, it's the probability of receiving a positive test. Question?
Could this be used to measure the accuracy of a test, like a gold standard test also?
So the question is, could this be used to measure the accuracy of a gold standard test? Not really. It's the accuracy of a gold standard test is kind of difficult unless you have an even better gold standard test. Gold standard tests, I think, are more usually determined by either by theory or by definition. It implies that you don't have anything better to compare it to. What we use this for regularly is for calculating positive predictive value and negative predictive value for a given test, and for calculating what the PPV and NPV will be when you apply it to different populations. Question?
So have they been using this a lot with like rapid HIV testing, like for OraQuick, to figure out like how good those tests are?
Have they been using this for rapid HIV tests such as OraQuick? I'm sure they have. Yeah, this is because screening tests tend to be tested in case control studies. So you'll take a group of, say, 50 cases, 50 controls, and you can calculate the sensitivity and the specificity of a test from that. But your performance in that case control is very different from what it's going to be when you take it out into the real world with low prevalence. So, yes. Quick question, does P of A given B equal P of B given A? No, no, no. The only case where that happens, you can see from Bayes' rule, is if P of A just happens to equal P of B. So here's an example of how not the same they are. What's the probability that you would retire given that you have as much money as Bloomberg? I don't know, for many people that might be high. I don't know, but what's the probability that you would have as much money as Bloomberg given that you retired? That's probably low. So they're different things. Okay, another exercise. for you here. Going back to the example we had from before of the pain, this imaginary study with a treatment and a control arm where individuals reported mild, moderate, or severe pain. Some calculations of probabilities here. What is the probability that an individual is in the treatment group? So probability that group equals treatment. No. Yeah, 0.5. Yeah. What about the probability that an individual in this study experiences mild pain or reports mild pain? 0.2. Yeah. Yeah, 20 out of 100. The probability that the individual reports mild pain given that they're in the treatment group. Sorry? Yeah, 15 out of 50, so 0.3. And the probability that an individual is in the treatment group given that they have reported mild pain. Yeah, 15, so these are all the people conditional on mild pain, narrows you down to this row, so it's 15 out of 20. If all of this makes sense to you, then you'll probably have no problem applying Bayes' rule and calculating PPV and NPV. Any questions? All right. We're getting a little low on time, so I think I'll let you work through this one on your own. It's worked out here. This is taking the example from before, the chlamydia example from the clinic, and just having you actually calculate the prevalence, the sensitivity, the specificity, the PPV, and the NPV. And note that here you can just calculate the PPV and NPV directly from numbers in the table, but you can also calculate them from these three numbers, actually just from, sorry, no, you do need these three numbers using Bayes' rule. You'll get lots of practice with this in the lab. And I actually have uploaded to Blackboard a little Bayes' rule calculator that's a spreadsheet shortcut that you can check out as well. Here are the equations that you would use to calculate them. The PPV calculation, and here I'm saying let's take the numbers from before and apply them. So from the 30% prevalence and apply them to the 3% prevalence case. The denominator in the PPV calculation is, let's see, is slightly complicated, just by the fact that to calculate the probability of getting a positive test, it is, so from here you could just calculate it directly. It is, let's see, positive, it's 58 out of 1,000, which is this 1 minus 0.097. I'm gonna show you a shortcut. There's a web page you can use for doing this, or you can use the spreadsheet. The spreadsheet is one that I made, but it's very useful too. This calculation, by the way, here is just directly out of Bayes' rule, and you'll have a chance to practice calculating that a bit by hand. That's all this web page does. It lets you do things like play with the prevalence, so you can plug in a certain probability of true positives, a certain sensitivity and 1 minus specificity, and see the performance of the test, the PPV. In a 30% prevalence population, it's 93%, and in a 3% population, it goes down to 50%. And you'll notice that, so going from, here is a sensitivity of 0.98, you can go up to 100%, and it doesn't really improve your PPV. In order to improve your PPV, you need to improve your false positive rate, your 1 minus specificity. Okay. So this is just that lesson again. This was the retiring in Bloomberg lesson. The probability of having the disease given a positive test result is not the same thing as the conditional probability in the other order. These are the big new definitions today: the sensitivity, specificity, PPV, and NPV. And these are definitely things that are going to be on your assignments and on the test, and not just calculating them, but I hope having some intuitive understanding of the relationship between them and with prevalence. Your new notation, we'll do lots of stuff with the probability notation as well. And I think we're done. Any questions? All right.